Okay, in this question we have this kind of block moving around, sort of like a tether ball a little bit, but there's also this string down here as well. And this block is just rotating around in a circle. If we were looking down from the top, it'd be like in a counterclockwise circle here, right? Um, and we want to know how fast this block is moving, and also what is the tension in this lower string right here. We're given some information, the mass of it, obviously some dimensions in this figure. We're also told that the tension in the upper string, this one up here, which I'm going to call T1, is 80 newtons, right? So this is T1 is 80 newtons. Okay. And we want to know, let's start with the tension in the lower string. So, tension's a type of force, right? So it would make sense to start with a free body diagram. And we have this in rotational motion, so we just want to take a snapshot of it, a convenient snapshot in time. I guess the snapshot that's shown would be most convenient, and then make a free body diagram from there. So I'm going to choose a coordinate system which has a positive y going upwards, but my positive x I'm going to have going to the left. This is because I know that I'm going to have some acceleration towards the center, and at this snapshot, this acceleration is to the left. So it'll just be nice if my acceleration is positive. So I'll set up a coordinate system like that for my free body diagram. And I'm interested, in this tension down here and the acceleration of the block. So it makes most sense to free body diagram this block. Okay. All right. So from a free body diagram with a block, with a coordinate system that looks like this, then forces we have acting on it, there's a weight, right? So there's mg. There's no normal force, it's not sitting on a surface or anything, but there are a couple wires attached, right? There's the tension 1 like this, and there's tension 2 like this, right? And I also know something about, the result of these, of all these forces. I'm going to have some acceleration over here. So I like to put that in my free body diagram as well. And it'll be a centripetal acceleration. Now, the next step we have, just like any other free body diagram, is tend to break into components and then sum the forces in each direction, right? So we need to break this into, we'll call it like a T1y and a T1x, and this will be a T2y and a T2x. Okay? So I'm going to take those two forces at angles and break them up into four forces that are just in the x and the y directions. But of course we need to know what that angle is, right? So take a look over here from our figure. We could say, all right, I'll make a triangle like this. And this is, we have this isosceles like this, so we know these are equal legs here. And so we can say this is halfway through, right? So this must be 1 meter here. I can make another triangle here that's 1 meter, right? So 1 meter, 1.25, I can get this angle here. And actually, I'm just interested in the sine and the cosine of the angle, right? When I break into components, T1y is equal to just T1 sine of theta, right? And T1x, this is T1 cosine theta, yeah? And these thetas will be the same thing for T2x and T2y. So really I'm interested in sine of theta and cosine of theta. Cosine of theta is the adjacent over hypotenuse, right? So that's this one, which I guess I don't have that, and divided by hypotenuse. But the sine of theta I do have. That's 1 over 1.25, right? That's sine of theta is 1 over 1.25. And cosine theta, I can go ahead and solve this from Pythagorean theorem. So this side here would be, I have 1.25 squared is equal to 1 squared plus, call this x squared, right? So x is equal to the square root of 1.25 squared minus 1 squared, right? And this comes out to 0.75. Okay? So cosine theta is actually 0.75 adjacent divided by hypotenuse 1.25. Okay? Or you can find theta. You can find theta from, definition of sine, right? Arc sine of 1 over 1.25. And if you want to find theta, this is equal to 53.13 degrees. Okay, so we'll break these up into components, and then I'll just leave it as kind of T1x and T1y, etc. And once I had them broken into components, I can sum the forces in the y direction, just like we've done with all of our other ones. We know the acceleration in the y direction is 0 because it's just going to go around in like a horizontal circle here, right? So sum of forces in the y direction is equal to 0 because the acceleration in the y direction is 0. And so we have sum of the forces in the y direction is going to be, this is T1y, which is T1 sine theta, minus T2y minus mg equals 0, right? Well, we actually know T1 was 80, and we know m and g, so we can actually solve for T2y. So T2y is equal to T1y minus mg. But T2y, this is T2 sine theta is equal to T1y, which is T1 sine theta. Actually, let me just go ahead and plug that in. T1 was 80. So this is 80 sine theta minus m was 4 times g is 9.8, right? And so we get the magnitude of T2 is just, well, instead of writing all this out, try to make the video a little shorter, I'll divide everything by sine of theta. When I divide this side over here, it just makes the sine of theta go away. So we have T2 is going to be 80 sine of theta minus 4 times 9.8 divided by sine of theta, where sine of theta is 1 over 1.25. Plug that in and calculate, or you can use the sine of 53.13, either way. But we end up here with T2 is equal to 31 newtons. And we just did it the same way that we've done other problems with summing forces, right? There's really, only really the new thing we're adding in is the fact that we can have a special acceleration related to speed, right? So you can maybe add another thing in there to solve. So for part B, they said, what is the speed of the block? Well, so how fast is this block going? I have to recognize that the speed of the block is related to the centripetal acceleration, right? I can get, v squared over r is my centripetal acceleration. So if I know the centripetal acceleration and I know r, I can find v squared. And r, very important here, r is the distance from, the object to the axis of rotation. So it's this distance along here. It's not along here. It's not along the string or anything like that. That's not, it doesn't rotate, it's not rotating around this way. It's rotating around in this kind of horizontal plane there, right? Around like this. And so that r is actually 0.75, what we already found. This r was my x value earlier, 0.75 that we got from Pythagorean theorem. Okay? For part B, we say that our sum of forces and the x direction equals mass times centripetal acceleration, so that's mass times v squared over r. And the forces I have in the x direction are just going to be T1x and T2x, right? So we have T1x plus T2x equals m v squared over r. So T1 was 80, so this is 80 cosine theta plus, what was T2 we just found? 31. So plus 31 cosine theta equals m times v squared over r. But, so we know cosine theta, that was actually 0.75, right? No, cosine theta is not 0.75. It's 0.75 divided by 1.25, sorry. Or you can use cosine of 53.13. Either way, we can get v from this as the square root of what we have here, r, which was 0.75, divided by m, which was 4 kilograms, times this 80 cosine theta plus 31 cosine theta, right? And so we end up with v is equal to 3.53 meters per second. So fundamentally, although it might look a little bit crazy at first, fundamentally it's just, take a snapshot for your free body diagram, and then it's just applying, Newton's second law, sum of forces equals mass times acceleration. You just have to recognize that, we have kind of a special acceleration here that is related to the speed. Well, it's not a special acceleration, it just happens to be because of this motion, we have that relationship between the acceleration and the speed and the radius.